Chapter 8 is about acids, bases, and oxidation-reduction reactions. Let's start by looking at the definition of acids and bases. So we're going to start with Arrhenius theory, which says that when an acid is dissolved in water, it produces H+. This H+ ion is actually referred to as a proton. Now this isn't the same proton that we were seeing inside a nucleus of an atom, that positively charged subatomic particle. This is just hydrogen with a positive charge. So the reason it's referred to as a proton is because it has a +1 charge, much like the protons in the nucleus, but there is a difference. So in this example here, we can see HCl, which is actually hydrochloric acid. When we add it to water, it dissociates into H+ and Cl-. So the fact that it produces that H+ ion, that proton, it is defined as an acid. For the definition of a base, it produces OH-, which is that hydroxide ion, when dissolved in water. So OH-, if you remember from your polyatomic tables, is called an hydroxide. So here we have sodium hydroxide being dissolved in water, and since it's an ionic compound, it dissociates into sodium+ and OH-. So the formation of this hydroxide ion, this OH-, is what defines sodium hydroxide as a base. There are other definitions of acids and bases because not all acids and bases fall under the same category. So the Bronsted-Lowry acid-base definitions are, for an acid, it's a species that donates a proton. Once again, the proton being that H+ ion. So in this example below, we have HNO3 donating its H+ to water. Okay, so the hydrogen here in this HNO3, it's giving that hydrogen up, and you can tell because when you go and look over at the product side of the reaction, we have NO2 by itself without a hydrogen attached. And the water now has an extra hydrogen, giving it a positive charge. The definition of a base for the Bronsted-Lowry definitions is not an OH- or a hydroxide formation, but an H+ acceptor. So in the same example above, water, H2O, is a base because it accepted a proton, it accepted that H+ from the acid in the equation. Once again, I want to point out when we're using the word proton in relation to acids and bases, we are not talking about a proton in the nucleus. We are talking about hydrogen losing an electron and forming a +1 charge. Let's now look at acid strength. So the strength of an acid is unrelated to the concentration. It measures the amount of dissociation. So basically, if an acid dissolved in water completely dissociates into its ions, it's going to be a strong acid. Same with a base. Weak acids and bases, they only partially dissociate. So how can you tell from looking at the chemical reaction? Well, looking at the top one, this strong acid, HCl, when it's dissolved in water, it forms H+ and Cl-. But notice the arrow. So we talked about equilibrium reactions. This arrow is strictly going from reactants to product. There's no reverse arrow, which means that dissociation is complete and it's not reverting back to the reactants. It's not an equilibrium reaction. In the weak acid example, we actually have acetic acid dissolved in water. And how do we know it's a weak acid? Because we see its ions on the product side, right? But the fact that it's equilibrium, that there's this reverse arrow here, tells us that it doesn't completely dissociate. It actually reverts back to the original reactants. Same thing applies with the two examples of bases below. So sodium hydroxide is a strong base because it goes straight to products. It completely dissociates. NH3, or ammonia, does not go straight to products. It is an equilibrium reaction, so it only partially dissociates. So here are just a few examples of some strong acids. So we have HCl, HNO3, and H2SO4. So HCl is called hydrochloric acid, HNO3 is nitric acid, and then this H2SO4, notice on this one, it's got 2 hydrogens. The other 2 strong acids didn't. So what that means, or that's referred to then as, is a polyprotic acid. Polyprotic, so the poly just meaning that it has more than 1 hydrogen, and that protic is like the proton, meaning it has more than 1 proton. Okay, so this actually means that H2SO4 can dissociate twice, essentially. So there's a few examples of strong acids. There are a few others that aren't listed here. So for strong bases, how to recognize those is that it's mainly the metal hydroxides. Okay, so sodium hydroxide and potassium hydroxide, and there's a few others as well. Here are a few examples of weak acids and bases. So if you were to dissolve these weak acids and bases in water, they would not completely dissociate. So we see acetic acid is a weak acid. Carbonic acid is also a weak acid. Notice what they have in common. A lot of carbons, oxygens, and hydrogens. For the weak bases, once again, we're seeing a lot of carbons and hydrogens. We have pyridine, aniline, and methylamine. Ammonia is also an example that we saw on a previous slide in the fact that it didn't completely dissociate. So let's talk a little bit about conjugate acids and bases. So by definition, a conjugate acid is a species that's formed when the base accepts a proton. So in the example below, we have HA on the reactant side. So we know that that's the acid because it has the proton, and acids are proton donors. So it has to have a proton in order to be an acid by that definition. Okay. B is just standing for the base. It could be any base. It could be a strong base, a weak base, doesn't matter. So the conjugate acid then is highlighted here in yellow. So when that base, that B on the reactant side, accepts a proton from the acid, it becomes positively charged, and the newly formed BH plus is the conjugate acid because it is the species that was formed when the base accepted that proton. Conjugate base then, well, that's your other product. That's the species that's formed when this acid loses its proton. So when that acid loses its proton, it now becomes negatively charged, and it is referred to as the conjugate base because it doesn't have its proton anymore, so it can't be an acid, so it's now the conjugate base. So let's look at the pH scale, because what the pH scale is, it determines the basicity or the acidity of all substances. So depending upon the pH, you can figure out, if you know the pH, if that substance is acidic, or if it's basic, or even if it's neutral. So how do we do the pH scale? Well, it's a scale from 1 to 14. So the middle ground, 7, is neutral. So our baseline is water, which has a pH of 7, because that's neutral. That's right in the middle of the scale. Okay, well, how do we measure the pH of water? We can do this because of autoionization. So what that means is, if you have water in a glass, beaker, doesn't matter, but notice I have 2 water molecules together. Well, what's happening in an equilibrium reaction, so you can see that equilibrium sign, is that a small, very, very small percent of water is actually donating a proton to the other water molecule. So when it does that, when one of the waters donates a proton to the other water molecule, we get a conjugate acid, the one that accepted the proton, of H3O+. We get a conjugate base, the water molecule that donated the proton, of OH-. So if it wasn't for this autoionization, we wouldn't be able to measure the pH of water, because in order to measure pH, we're measuring the concentration of that H3O+. So if H3O+ didn't form, pH could not be measured. So we're measuring the concentration of those protons, those H pluses. And by measuring that, we can figure out the acidity or basicity of a solution. And it does go from 0 to 14. I've never actually seen something go below 1. That's why I said 1 to 14, but I'm sure there is a case. So to the left of the scale, anything below 7 is going to be acidic, anything above 7 is going to be basic. So in order to calculate pH, we have an equation, right? So to calculate pH, since pH is dependent upon that H3O+, the concentration of H3O+, that's part of the equation. These brackets around H3O+, that's indicating that we're looking at the concentration. When we're talking about concentration, as we saw in Chapter 6, there's many different ways to calculate concentration. And the way that we're using it in this equation is we're using molarity, so capital M, where we have moles of the solute divided by liters of solution. So it's most often used in chemistry. When we calculate pH, I want you to know that it's not always a whole number. It can have a decimal point, okay, so be aware of that. When you're entering this into your calculator to solve, do not forget that negative sign. Okay, you're going to push the negative sign first, not the subtraction sign, but the negative sign. Then you're going to find the log button on your calculator, parentheses should appear, and then you can enter the concentration of H3O+, which will be given to you in the problem itself. And I've worked through some of these problems step by step on a different video, so you can refer to that. When you do solve for pH, keep in mind there are no units, so it's just a number. All right, another thing to point out, looking at the very bottom here, is H3O+ is the same as just H+. So you'll see both of these variations depending upon what video or book you're looking at, and they're interchangeable. They mean the same thing. Okay, so when you're approaching a question, if they give you the H+ concentration, that's fine. That's the same as H3O+. So number 1 here shows how we're going from molarity, or concentration, of the H+ ions to pH. So this was the equation that we saw on the previous slide. Well, as you know, we also like to do reverse. So the reverse of this would be calculating the concentration of the H+ ions based off of the pH. So to do this, we're going to be taking the pH and we're raising it to the power of 10. So this is how it looks in your calculator. So it's 10 to the power of, and once again, don't forget that negative sign. So by doing this calculation, you're going to be able to, based off of the pH, figure out the concentration of the H+ ions in that solution. Here are the problems I will be working through on the supplemental video. You'll notice I have the equations that you need to solve these problems listed on the bottom. So one for solving for pH and the other when they're asking for the concentration of H3O+ ions. So in the first problem, you are using the pH equation and you are given the concentration in molarity, which is what you wanted in. The second two problems, notice they want the concentration of those H+ or H3O+ ions. It's written two different ways, but they're asking for the same thing. Remember, those two are interchangeable, so you are using this second equation to solve for number 2 and 3. You are given the pH of both, so you are going to raise that to the negative power to solve. And I work through exactly how to do that on your calculator in the videos. So why is pH control important? Well, as you can see, it's important in several different areas, in several different fields. In agriculture, crops grow best depending on the pH of the soil. You can even bring it down to a smaller level. When you're gardening, right, the pH of the soil is going to affect how well your flowers grow or your vegetables grow. You can even change the pH to make the blooms on different flowers be different colors, hydrangea being one of them. If you have more basic soil, you're going to get blue flowers. If you have more acidic soil, you're going to get pink or red. Physiology is another area. So if the pH of our blood were to shift by just 1 unit, we would die. So we need a pH control of our blood. We need it to be in a specific range. And we're going to look at how our body does that later on in this chapter. Industry also needs it for manufacturing purposes. You don't want to put a skin cream on or a lotion on if it's acidic, right? So they need a pH control, and they need, when that material disintegrates, for the pH not to change. Municipal services, drinking water, treatment of sewage, right? We don't want acidic drinking water. We also don't want basic drinking water. We need to keep it right around that pH of 7. And last but not least, acid rain. So what acid rain is nitric and sulfuric acid that's formed through reactions with emissions in the air, right? Everybody's driving around, you have that exhaust. It's actually forming nitric and sulfuric acid in the air. And now, when I say acid rain, this doesn't mean that if it starts raining and lands on your skin, it's going to burn your skin. Okay, it's not that acidic, but it does affect our everyday life because it's making the streams more acidic. So when that rainwater falls into lakes and streams, even oceans, it can lower the pH of that water, affecting all aquatic life living in that lake or stream. All right, so let's look at a neutralization reaction. So what a neutralization reaction is when we have an acid and a base. During neutralization, the acid reacts with the base and they form water and salt. Okay, so these are always the products. So you always have an acid and base as the reactant, and you always have a salt and water as the products. And so remember that reaction scheme. You will probably be asked, what happens when you add an acid and base together? What are the products? And your answer should be, oh, well, a salt and water. In this specific one below, we have sodium hydroxide, which is a strong base, reacting with hydrochloric acid, which is a strong acid, and they are forming NaCl, sodium chloride, right, table salt, and water. So now let's look at buffers. So we talked a little bit about pH control and how different areas need pH control for different reasons. Well, a buffer helps with pH control. So the definition of a buffer is that it resists any changes in pH. So if I had a solution and I added an acid to it, but I had a buffer in the solution, what that buffer does is it resists any changes in pH by reacting with that acid in some way. I'm going to look at a few examples of that. Buffers are used to obtain optimum pH. And our blood actually has a natural buffer solution so that we can maintain a pH of approximately 7.4. So and what this buffer is bicarbonate. It's bicarbonate buffer system. So we have carbonic acid in our blood, believe it or not. It's a weak acid. And how do I know it's a weak acid? Equilibrium sign. Okay, and it's not completely dissociating. When it does partially dissociate, it dissociates into a conjugate acid, so that's that H plus ion by itself, and a conjugate base, which is HCO3. So it's basically carbonic acid, but with one less proton. So let's look at how a buffer works. We said that the reason for buffers is you're trying to resist any changes in pH. So how does a buffer do that? Well, it does that by establishing an equilibrium between a weak acid and a conjugate base, much like the example below. So we have a weak acid dissociating into its conjugate base and a conjugate acid. Well, why do we need a weak base? Because we need that equilibrium. The equilibrium is what's key, because we're going to be using Le Chatelier's principle, which applies only to equilibrium systems. And his principle is that if we disturb that equilibrium at all, that's okay, because the equilibrium is just going to shift in whichever way it needs to fix that area. So if we take something away, the equilibrium is going to shift to replace what we took. If we add something, the equilibrium is going to shift to get rid of the excess. So if we add a base, for example, what's going to happen is that base, that OH minus, is going to react with H plus to form water. So if that OH minus is reacting with H plus, that means our concentration of H plus is going down. All right, well, if that H plus goes down, what's going to happen? Equilibrium is going to shift toward H plus to form more of it. And remember, H plus determines the pH of a system. The concentration of those H plus ions, that's equals the pH. So as long as we can replace those H plus ions that are being taken away, we can maintain the pH. All right, well, what if we add an acid? Let me erase this. If we add an acid, well, acid is H plus ions. So that means we're increasing the concentration of H plus. So if we're increasing the concentration of H plus, the equilibrium is going to shift in the opposite direction towards carbonic acid to get rid of that excess H plus, maintaining the pH where it was. So now we're going to look at the buffer system present in our blood. And notice the buffer system I have below has two equilibriums going on at the same time. So I have two equilibrium arrows. CO2 and water forming carbonic acid, and then carbonic acid dissociating into H plus and HCO3, and there should be a minus sign here. Okay, so we want to maintain our pH between 7.35 and 7.45. That's normal pH. If we go lower than that, so lower than 7.35, we can get what is called acidosis. And so we're going to look at this example first and see how exactly that happens. So acidosis is caused by high CO2 concentrations. Okay, and high CO2 concentrations can lead to high H plus. So H plus being those acid ions, those protons that determine pH. All right, so how does this happen? Let's start all the way in the far left of this equation. So I just said high CO2 concentrations. So if you have high CO2 concentrations, it's going to be from emphysema or pneumonia, anything like that. So if you increase our CO2, concentrations of that go up. What happens to this equilibrium is it's going to shift to the right to get rid of that excess CO2. And that's all well and good, but when it shifts to the right and gets rid of that excess, what it's actually doing is it's making more carbonic acid. So that means our concentration of carbonic acid is then going up. And those high concentrations of carbonic acid is going to affect our next equilibrium. Because if we have high concentrations of carbonic acid, this equilibrium here is going to shift to get rid of the excess. And it's going to shift to the right towards H plus. So it's getting rid of that excess carbonic acid, shifting that equilibrium to the right. And what that's doing is it's making that concentration of those H plus ions go up because we're making more of it. So since we have more H plus ions, we now have a low pH because of that high concentration, and that is what can lead to acidosis. So let's look now if we had low concentrations of CO2. So low concentrations, that means the pH is increasing. That can be alkalosis. Too high could be very bad. So this often can happen with hyperventilation. You can get low CO2. You're just not breathing in. So let's look at our equilibrium and see what happens when we have low concentrations of CO2. So this time our CO2 is low, so I'm going to put a down arrow here. All right, well, what that means is equilibrium is going to shift to make up for those low concentrations. So this time equilibrium is shifting to the left. When it shifts to the left to replace that CO2, what happens is the concentration of carbonic acid is going down, because in order to make more of that CO2, we're using more of the carbonic acid. So the concentrations of carbonic acid are now low. So the next equilibrium is going to shift to make up for that. So it's going to shift to the left so that we're making and replacing that carbonic acid that we're losing. Well, what happens then? In order to make that carbonic acid, the concentrations of H+ and the bicarbonate are both going down. But it's the concentration of the H+ which is affecting the pH in our blood. Because if we have low concentrations of H+, that means our pH is going up. We're having a high pH due to those low concentrations. That high pH is what leads to alkalosis. Indicators can indicate the pH of a solution by changing color. So in the lab where we did a titration and we're trying to figure out the concentration of acetic acid in vinegar, an indicator was used to find the endpoint of that titration. So that indicator specifically turned pink when it was basic. So when we were adding the sodium hydroxide to the vinegar, when that vinegar started turning pink, it was indicating that that solution was going to be basic soon. Okay, so different indicators change different colors when in an acidic or basic environment. So there's a variety of them that can be used depending upon what conditions you want to apply them to. Indicators can even be soaked onto thin paper strips. So I have a picture of this off to the right here. And what that does is notice it has a pH scale going from 0 up to 13. It should actually be going up to 14, but that's okay. So depending upon the color, when you dip this paper strip into a solution, you can figure out its acidity. So if on this particular indicator, if it's pink, it's going to be acidic. Right? Orange, a little less so, yellow, even less, and then we have neutral 7 being green. And then as it changes towards the blue, you're seeing basic conditions. So now we're going to look at oxidation reduction. Oxidation reduction is often referred to as a redox reaction, and we've looked at these in Lab 9. And what a redox reaction is the transfer of electrons from one reactant to another. Oftentimes, redox reactions are single replacement reactions, where we have a metal or element by itself replacing a metal or element that's in a compound. So the first thing you want to do when approaching a redox reaction is figure out the charge of all elements in that reaction. Whenever we have an element by itself in its pure form, so not in a compound, its charge is 0, it's neutral. So for magnesium on the reactant side, since magnesium is all by itself, the charge on magnesium is just 0. Going to the product side of the reaction, we have copper by itself. Since copper is an element by itself, its charge is 0. The only compounds or elements that will have a charge are the ones that are in a compound. So looking at this copper sulfate, it's an ionic compound. So we're going to have a -2 on the sulfate. I can figure that out by looking at the polyatomic tables. And that means that copper is going to have a +2 charge. Because this compound is neutral, the +2 and the -2 need to cancel each other out. On the product side, magnesium is now in the compound. So now that magnesium is in a compound, it's going to have a charge. Its charge is also going to be +2, just like copper. That we can find by looking at a periodic table. But we also know it needs to be +2 because the sulfate is a -2. And they need to cancel each other out. So you look now at the ones that are changing. So copper is a +2 on the reactant side. On the product side, copper is now 0. So since copper's charge has changed, it is either oxidized or reduced. We just need to figure out which. In oxidation reactions, reductions and oxidations happen in pairs. So one element is reduced, the other element is oxidized. What reduced means is that we're gaining electrons. So where are we gaining those electrons from? We're gaining them from the element that was oxidized, because the definition of oxidation is losing electrons. So you need to find the two elements where the charges changed, because their charges changed because one lost negatively charged electrons and the other one gained those electrons that one lost. So copper went from a +2 to a 0. So he's definitely involved in this redox reaction. Looking at the sulfate. Sulfate's -2 on the reactant side, and it's also -2 on the product side. So since the charge of that sulfate ion stayed the same, it was not reduced or oxidized. So we're just looking for the elements or compounds that have changed in their charge. Magnesium, however, did change. It went from 0 on the reactant side to a +2 on the product. So now we have our pair, copper and magnesium. So let's see which one is reduced and which one is oxidized. So copper went from a +2 on the reactant side to a 0 on the product side. So how do you go from a +2 to a 0? Well, you're gaining 2 negatively charged electrons. To get to 0, you're going from a +2, adding 2 negatively charged electrons, and that will give you 0. When you are gaining electrons, that means that is the element that was reduced. So reduction is gaining electrons. So since copper gained electrons from reactant to product side, copper was the one reduced. Since they happen in pairs, I can assume that magnesium is the one that was oxidized. But just to prove it, we see magnesium went from a 0 to a +2. How do you go from a 0 to a +2? Well, you lose 2 negatively charged electrons. So we have copper being reduced and magnesium being oxidized. Now, you might also need to answer the question of how many electrons are involved. And to do that, you look at the charges. Right? To go from a +2 to a 0, you need 2 negatives. So that's why 2 electrons are involved. Another question you might need to answer is which one is the reducing agent and which one is the oxidizing agent. So the rule is the one that's oxidized is the reducing agent, because in this case magnesium is the element that is reducing copper. So it's called the reducing agent. The one that's being reduced, in this case copper, is then the oxidizing agent, because copper is oxidizing magnesium. So here are some ways to remember the definitions of oxidation and reduction. So some mnemonic devices that you can use. So the first mnemonic device I have here is oil rig. And what this stands for, O for oxidation, I is, and then L for losing. So oxidation is losing electrons. So if you lose electrons, you are oxidized. Reduction then is gaining electrons. Another mnemonic, the one that I usually prefer, is Leo the lion says grr. So it's the same thing. Losing electrons, oxidation. Gaining electrons, reduction. There's also a number line way that I like to use that you'll see me use in the videos that might help as well. So pick which one works for you and stick with that method. So here we're just looking at the definitions of oxidizing agents and reducing agents a little bit closer. So an oxidizing agent causes the oxidation. So that's why the element that is reduced is the oxidizing agent, because they're causing the oxidation of the other element. Reducing agents then cause reduction. So in the example below, copper oxide is reduced. In that case, copper is reduced. So if copper is reduced, copper is the oxidizing agent. we have hydrogen being oxidized. It's going from a 0 to a +1. So since it is the one that is oxidized, it is referred to as the reducing agent because it is reducing the copper. Over to the right, I have the half reactions just to show. We have a +2 on copper. It's going from a +2 to a 0. To go from a +2 to a 0, it needs to gain 2 electrons. Hydrogen then is going from a 0 to a plus. That should not be a negative sign. 0 to a plus, so it is excuse me, losing those 2 electrons. So for oxidation and reduction, another way to identify it is that for reduction to happen, you are either losing an oxygen, gaining a hydrogen, or gaining electrons. So these are all different definitions of reduction. We've looked at it just in the electron way because that's usually the most reliable way for all examples and applies to all. Because not all reaction equations have hydrogen in them or oxygen. So looking at the electrons is going to be the more foolproof way. For oxidation then, if you see gaining of an oxygen, oxidation is occurring. If you see losing of a hydrogen, oxidation is occurring. Or you can look at the electrons and figure it out from there, which is the approach we have taken.